Okay, so good morning to everybody. Today we're going to continue with our discussion of indefinite integrals. I want to say something about integrals before we do some more examples. As I said before, there's no real algorithm to solve integrals. There are various methods, and when you get more and more experienced, you kind of get intuition as to which method is the best to try when you get an example. But it's very, very important to practice a lot of these integrals. It's not like derivatives, and not like limits, and not like using L'Hopital, which all require practice, but once you get the idea, that's it, it's yours. And if you do 10 examples and you got the idea, that's fine. With integrals, it's really important to do hundreds of examples, because that's the only way to master all the little techniques, and then when you get the next example, you can be quite confident that you're going to know what to do. So it's really important to practice doing a lot of these, and I literally mean hundreds. Open any calculus textbook you find in the library. At the end of each section, you will find practice exercises. So do 50 of them about integration by parts, and 50 about partial fractions, and 50 about substitutions, which we're going to discuss today. And then do at the end of the chapter all the mixed examples. It's really important to practice these in order to really know how to handle them. Okay, so what we were discussing last time, we were still in the middle of discussing examples of integrating rational functions. And let's just continue our enumeration of the examples from last time, because they're really just more examples of the same idea. So I'm going to call this example number 16, if I'm not mistaken, and we were actually on 15 last time. Okay, so the example that I want to do now is the following. I want to find the antiderivative of 1 over x squared minus x plus 1. Now this is again an example of a situation where the denominator is a quadratic factor that's not irreducible. Okay, so if you try to break this into linear factors, you see that it won't work. In other words, it doesn't have real roots. Okay, and another standard kind of manipulation that can be done in a situation like this, and that's what I'm going to demonstrate now, is the following. So we would like to somehow formulate this and get it into the form of something that of a derivative of arctan. Okay? 1 over x squared plus 1. It's not going to be exactly that, but it's going to be similar. And what I'm going to use is the following identity, namely, if you have x squared plus px plus q, where p and q are any, let's say, integers, then that can be rewritten as x plus p over 2 squared plus q minus p squared over 4. There's nothing deep here. If you just open the parentheses on the right side, you'll see that you get exactly the left side, right? You have x squared plus 2 times p over 2x, which is px, plus p squared over 4, which cancels with this, and you get the q. Does everybody see that? So this is just an identity, but there's nothing deep going on here. So in our situation, we have x squared, the p is minus 1, and the q is 1. Do you see that? P is minus 1 and q is 1. So in our situation, we get that x squared minus x plus 1 can be rewritten as x, p is minus 1. So you have x minus 1/2 squared plus q is 1, p is minus 1, so minus 1 squared is 1, divided by 4 is 1/4. 1 minus 1/4, you just get 3 over 4. So does everybody agree to this side calculation or side remark, which justifies the following, and we'll see in a minute why we want to do this. So I'm going to replace this with this. So I get x minus 1/2 squared plus 3 over 4. Good? The reason for doing this is that I'm gradually heading towards something of the form 1 over something squared plus 1. That's the derivative of arctan, right? So I'm still not there yet because I have 3/4 here, and I want to just have 1. So how do I make a 3/4 into a 1? I multiply by 4 over 3. I can't just multiply this by 4 over 3. What I can do is multiply the top by 4 over 3 and multiply the bottom by 4 over 3. Do you agree that that's legitimate? Okay. So the 4 over 3 with which I'm going to multiply the top, I'm just going to write outside. Okay? So I'm going to get 4 over 3. That's multiplying up here. And then I'm going to multiply down here by 4 over 3. So I'm going to get the integral dx over. When I multiply this by 4 over 3, I get this plus 1, which I desired. That's good. But now I have to multiply this by 4 over 3. And I want to leave it as something squared. I don't want to ruin that. So I want to throw the 4 over 3 inside this squared. So I'm going to multiply inside by 2 over root 3. So I'm going to get here 2 over root 3 times x minus 1/2. And all of this squared. Did everybody follow? Okay, nothing deep. Good? You didn't follow?
I didn't follow.
So you have, okay, so let's go from this step to here and see if you believe me. 2 over root 3 squared is 4 over 3. Do you agree? 2 over root 3 squared is 4 over 3. So I can pull that out. And then if I want to pull out a 4 over 3 from the entire denominator, I'd be left with, instead of this 1, with a 3 over 4. Right? So 4 over 3 pulls out of the entire denominator, out of the integral, cancels with this, and I just get this left. Do you agree to that? Just algebra. Okay? So I did it the other way around. Okay? Okay. If somebody's confused because we just started and it's morning, just go over it again later, calmly, over coffee, and I trust you will be able to figure it out. There's really nothing sophisticated going on here. Okay, once I get to this step, that's it. It's of the form 1 over something squared plus 1. That's precisely the derivative of arctan of whatever's inside here. So it's arctan of ugly. 2 over root 3 x minus 1/2. Now we have to, of course, fix this. Okay? So how do we fix it? So the derivative of arctan of this thing is 1 over this squared plus 1. That's good. But now there's an inner derivative, 2 over root 3, which we don't want. So we multiply by root 3 over 2. And then there's this 4 over 3, which I can't just ignore. So I'm going to write that here. And finally,
Plus C.
thank you. Plus C is asleep. Thank you for the substitute. So plus C. Okay? Good. So the idea is to get from an expression to a equivalent expression, which is of the form something squared plus 1. Okay? So this is example 16. Example 17 is the following. Suppose we have the integral of minus x plus 2 divided by x squared minus x plus 1. Still exploring the situation where the denominator is a quadratic irreducible factor. So we did something very similar to this. Okay? We want to have the derivative of the bottom on the top. Then it's ln. So here goes. I want to have x squared minus x plus 1. On the top, I want to have just 2x minus 1 dx. This would give me precisely ln of the bottom. Do you agree? Because of what we said last time. But that's not what I have here. These are clearly not equal, so I have to fix them. So I'm taking the blue so you can see this is what I wanted, and everything else is going to be fixing it. So I had here minus x. Here I have 2x. So I'm going to multiply by minus 1/2. Now I have minus 1/2 times 2. That's minus 1. So the x's are now the same. Now I have minus 1/2 times minus 1. That's plus 1/2 of the free coefficient here. But here I have plus 2. Plus 1/2 plus 2. So I'm going to add 3 more halves. Of what? Of 1 over x squared minus x plus 1 dx. And now they're precisely equal. Okay? We did this for an easier example last time. I think it was example 15, which was what we left over in example, I don't know, 11 or 12. Look back in your notebooks. Okay, we did a very similar manipulation to complete the numerator, to make the numerator into the derivative of the denominator in order to get an ln and then see what's left over. So now what we get, so this is minus 1/2 ln of the bottom in absolute value, precisely, because that's exactly how we set it up, plus 3 over 2, and now I have this thing to handle. Okay? In the last example last time, once we got here, it was easy. It was automatically an arctan. In this example, it's not. You still have to work on it. But this is precisely example 16. We already did that. Look at the previous board for a second. This factor is precisely example 16. Okay, so I'm going to write 3 halves, and then I can either just write all that expression that we got here. Remember, it was kind of long, this thing. Look here a second. Look on this board, Ami. This expression, remember, this was exactly this. So I can either plug this entire thing into there, or be very lazy since I just wrote it. So I'm going to write plus 3 halves of 16. Questions? Remark, I can see in the eyes of some people sitting here that they're Cookie Monster eyes. You know, like, ooh. Do you know Cookie Monster? Yeah. That means that they're still a step behind and wondering, whoa, what's going on here? Okay? So I can't do every example 3 times. Okay? If there's one single step that's not clear, I'd be happy to explain it again. But what you have to do is go and start practicing. All the little techniques, all the little details. Go over what we did last time. And you'll see that there's nothing tricky going on here. It's just standard kind of things that you do. Okay? Yes, question?
How'd you go from, in note 17, how'd you go from the first step to the second step?
From here to here?
No.
From here to here?
Yes.
I wanted to have the derivative of the bottom sitting on top because that's exactly the derivative of ln of the bottom. I wrote it. But then it wasn't the same as what I started with, so I fixed it. I multiplied here by minus 1/2, to fix the 2, I get just 1. Sorry, minus 1. Now the x's have the same coefficient. Do you see that? And then I have plus 1/2 here, plus 3/2 here, so that's plus 2, and now they're precisely equal. Okay? Precisely the same thing that we did in example 15, which was the last example last time. Okay? Okay, example 18. So, example 18 is going to be the last example I want to do of integrating rational functions. And it's going to be this one. So now the denominator is actually of degree 3. You're not likely to get many of those, because remember, in general, we don't know how to find roots or how to factor polynomials of degree 3. There is a formula, most people don't know it, right? And finding the roots, therefore, is kind of hard, so usually you won't get things like this. But in this case, it is possible, because one of the root just looks at you. So which is the root that just... Negative 1. It's very obvious that negative 1 is a root of this polynomial, right? Does everybody see that? So that means you have a factor of x plus 1 here. You can divide the polynomials and see what the remaining factor is. Okay? So what you get once you observe that is the x over, so there's going to be an x plus 1, which is the one which we just observed, and the other factor is going to be x squared minus x plus 1. Here? Well, the plus c lives inside this, so you can write it or not write it. Never write anything like this. I'm just being very uneducational here and lazy. Okay. Okay. So what we got here now is a product of two factors. One is a linear factor. The other is an irreducible quadratic factor. Okay? What we're going to do, just like in all the previous examples, we're going to do partial fractions. Okay? And again, it's going to take a certain twist. So whenever you do these partial fractions, it depends on the situation of the denominator. So the partial fractions here are going to be 1 over x plus 1, x squared minus x plus 1. This is what we're partial fractioning. Is going to become of the form a over the linear factor. That's what we had when we have a linear factor of multiplicity 1. There's only one of it. Plus, there's going to be a bx plus c divided by the irreducible quadratic factor. Why is this what you do? That's the theory. That's the mysterious theorem that I'm not spelling out precisely, which tells you if this is the situation, this is what you do. If that's the situation, that's what you do. So if this is the situation, this is what you do. Okay? Just a constant for any linear factor. If the linear factor has multiplicity, I'm reminding you for last time, there's going to be another constant over the linear factor squared. Remember we had an example like that? And if there's a quadratic factor, irreducible one, it's going to have a bx plus c. Okay? And now you have to solve this, right? So you're going to get, how many equations are you going to get here?
3.
There are going to be 3 equations, because the equations are going to be of quadratic polynomials, right? There's going to be a times this. Do you see that? So you're going to have an equation for the x squared coefficients, an equation for the x coefficients, and an equation for the free coefficients. So you get 3 equations. I'm going to write it ... You can try solving it. It's just tracing the very same ideas, nothing interesting, so it's not really worth the time. And what you get is a equals 1/3, at least that's what I got, b equals minus 1/3, and c equals 2/3. Okay, so all of this is the side calculation of the partial fractions, which I didn't write all the details for. But please make sure you know how to do this. Okay? So this is the reason for this step, which I'm going to write on the next board. I'm going to replace this with this, writing 1/3 for A, minus 1/3 for B, and 2/3 for C. So what I get is, I get 1/3, that's the A, dx over x plus 1, plus, and I can again pull out a 1/3, minus x plus 2 over x squared minus x plus 1. So this is the partial fraction step. Okay? This in turn equals 1/3. What's the integral here? What's the antiderivative? ln of the absolute value of x plus 1 plus 1/3. What would you do with this one? Right, write 17. And we're done. Okay? Now, in previous iterations of teaching this course, I actually started from example 18. So when I got to this point, I had to solve this, which would involve example 17. And then inside example 17, I had to solve example 16. And by the end of solving example 18, I'd have a bunch of dead students. Or not dead, but... Okay. So that's why I broke it up into intermediate examples, each one hiding only one trick, only one kind of new method. But you can see that examples can get, complicated. Okay, not hard. There's nothing difficult going on here. There's nothing, magical going on here. We're not using any heavyweight theorems. We're just doing standard calculation tricks. If you master the little tricks, you can do these things without much. It's going to take a bit of writing, but you don't need a lot of creativity to do it. Okay? So this wraps up this example, and that's all I wanted to say about integrating rational functions. Okay, so you basically, the algorithm tells you, first, if the degree of the numerator is greater than the degree of the denominator, divide the polynomials. Then you get the remainder, which is of the form degree of the numerator less than the degree of the denominator. Then you do partial fractions according to the factors that appear in the denominator, and we saw several examples. And then you get to things that are either derivatives of ln's or derivatives of arctans, which require some intermediate fixing, or derivatives of things like x minus 1/3 squared, which is the derivative of x minus 1/3 in the denominator. Remember we had that? So those are the three things that show up, and it's just an algorithm. A boring one, in fact. Okay? Okay. Good. So the next thing, the next method for doing integrals is called substitution. So maybe we'll start on a new board. So substitution. There's a theorem here. I want to write the theorem, but I want to write it after we do a couple of examples, because the theorem is actually more confusing than it should be. It's clear to understand what you're doing and then see why the theorem is really just saying that. Okay, so I'm going to start with examples. Suppose we want to do, let's just continue our enumeration. It looks like we're doing a lot of examples this way, doesn't it? Okay, 19th. So we want to do the integral of e to the x divided by e to the 2x plus 1. It's not a rational function, so none of the previous sort of examples are relevant here. You could maybe try doing some form of integration by parts. But really what you want to do is you really want to replace this e to the x by, let's call it t. Okay, e to the x is the annoying thing here. Okay, so we want to replace it by t. There are various ways of writing this. I'm going to present the one I'm used to, but there are other ways. So I'm just going to write t equals e to the x. And I'm writing this underneath a long equal sign to indicate that this is the justification for this step. Okay? So I'm replacing e to the x by t. What do I get? I get here the integral. E to the x is just t. E to the 2x is t squared, right? So I get t squared plus 1. And now I can already see that this is going to be nice and friendly, right? It's, for example, a rational function, right? I can right away see that the derivative of the bottom is on the top. This is going to be manageable easily. But this is not correct. There's an extra twist to it. And the twist is that there's this dx here, which, remember we said this is just part of the notation, right? But in fact, when we're doing change of variables, we can't just write here dt and move on. Okay? And the reason is that there's a theorem behind it, which I'm going to write in a few minutes. But what we do, the technical step, what we do in order to make this correct, is we take the derivative of this, which happens to be just e to the x, and add the dx, and say that this equals the derivative of this, which is just 1 dt. Okay? Now, everything written here under this equal sign is, I don't have a better word than nonsense. This is nonsense. What does it mean e to the x dx equals 1 dt? How can you compare two things in different variables? Even that doesn't compile. And how can you put in this dx, which is just part of the notation, and write an equation with these somethings? In fact, you could formalize this. There is a notion of differentials, which we didn't really get into. But at least for us, this is really nonsense. Do you agree? You can't write this anywhere else in this course other than under an equal sign in parentheses in order to justify a substitution. Okay? It just doesn't make sense otherwise. Okay? So did everybody understand what I did here? Why I did it is going to follow from the theorem. But do you understand what I did? Yes? Okay. So now this tells me that in fact, e to the x dx is going to be replaced by dt. So e to the x dx is going to be replaced by dt. So I'm just going to have dt here. Is it clear? Everybody? Okay. So now, what is the antiderivative here? It's even easier than we thought. It's just arctan of what? Right, it's arctan of t plus a constant. And now there's an extra step. The extra step is going back to the original variable. We can't have the antiderivative of a function in x suddenly be a function in t. And in fact, there's a missing c here, right? And it's not the plus c, arctan. And in fact, the derivative of this is not that, right? So going back to the original variable is just plugging in for t what we had for it in x. So this is equal arctan of e to the x plus c. And now we're done. And in fact, remember, we can always verify what we did by taking the derivative. What's the derivative of this thing? It's 1 over this thing squared plus 1 times the inner derivative, e to the x. It's precisely this. Do you see that? Good? Everybody? Questions? Okay. So let's do another example of this. And then we'll write down what the theorem actually says. So example 20, let's do the integral of 2x e to the power x squared dx. So again, I'm going to do a substitution. This time I'm going to substitute t equals x squared. Okay, I'm going to have this x squared equals t. In which case, I'm doing as before. 1 dt equals 2x dx. Is it clear what I'm doing? Okay? And what do I get? So the 2x dx is what becomes the dt, and then e to the x squared is just e to the t. Good? Okay. So now I get the antiderivative is just e to the t plus c. And now I have to go back to the original variable. So it's e to the x squared plus c. Some of you, if you have been practicing already at this point, might even say, bless you, you didn't really need to do this. I see right away that this is the derivative of e to the x squared. It's an immediate integral. And that's fine. If you see it, if you see that this is an immediate integral, that it's just the derivative of this, because it's this times the inner derivative, that's fine. Okay? If you don't, maybe you need this substitution or any other method which works. Okay? So let me write what the theorem says. The theorem is kind of a dual to the chain rule. That's how you prove it. You start from the chain rule. Remember, we saw integration by parts, and we saw that it was a dual to the product rule for derivatives. Remember? That's how we kind of formulated it. And in fact, substitution is a dual to the chain rule. I'm not going to go through the details, because from my experience, they confuse more than they help. So I just want to write the formula. Okay, so the formula for substitution is also called change of variables. That's a name for the same thing. So what it says is basically the following. If x is a function, but I'm not going to use the letter f, because that's going to be the function that we're integrating. So I'm going to use the Greek f, which is called phi. So if x is phi of t, and we need it to be, this function we need to be differentiable, because we're going to take its derivative, and maybe you can weaken the conditions somewhat, but I'll just require it to be invertible. Then the integral of f of x dx equals the integral of f, instead of x, I'm writing phi of t, because x is phi of t. But now I'm not just writing dt, I'm adding here phi prime of t, and then I'm writing dt. So this is the formula. Let's put it in a blue box. And I know that many people get confused by this formula, So let's do now one more example, or two more examples, after we've seen the formula and see that really this is what we're doing. This is really the nonsense under the long equal sign. Okay, so let's do another example. So, example 21. Let's do the integral of root x divided by x plus 1 dx. And since x is sitting under a root, we're going to require x to be positive. Okay? So here's what I'm doing. And I'm going to do it the way we did it in the previous examples, but I'm going to show you that it's actually what the theorem is saying. So what kind of... I mean, this thing is looking at me and telling me, hey, use a substitution. Substitute what?
Square root of x.
Right. Substitute square root of x equals t. It really calls for it. Do you agree? Yep. Now, I'm going to rewrite this as if t equals square root of x, x equals, let's write it the other way around, x equals t squared. Do you agree that this and this are the same thing when x is positive? Do you agree? This is the phi of t. This is the phi of t that we're looking at. This is phi of t. The t squared. And now, the formula tells us, let's look at the formula again in this box. You're going to replace x by phi of t. We'll do that in a second. But you're going to replace dx by phi prime t dt. So that's the nonsense under the equal sign. I'm going to write, instead of dx, I'm going to write phi prime t dt. So back to here, if phi was t squared, then phi prime is 2t, and then 2t dt is dx. Do you see that this is precisely what the formula in the substitution theorem tells me to do? Do you see that? And since phi is invertible, you can do it in both ways. So I wrote here t equals root x, and then replaced it by x equal t squared, so it will really fit precisely into that formula. But in the previous examples, we did it at this level. We said, okay, dt is the derivative of this dx, which is also fine. Both ways work. Okay? So let's see what we get here. Let's carefully do all the substitutions. Instead of root x, I'm going to write t up there. Instead of x plus 1, I'm going to write t squared plus 1. This is f of x written as f of phi of t. Do you agree? And now instead of dx, I'm going to write 2t dt. Do you see that this is precisely the formula that we just wrote? Everybody? Good? Okay, wonderful. And now we have to solve it for t. So what we have there is what? Well, there's a t squared here. 2t squared. So let's, how did I do it? Yeah, okay, so 2t squared over t squared plus 1 dt. That's what I want to solve. And any suggestions?
We can divide just simply.
Okay, you can divide and run through the entire algorithm of rational functions. Any other suggestions?
Yeah. You got a t squared from the denominator. Take it to the side.
Okay, look what's going on here. I just got 3 different suggestions to solve the same integral. That usually doesn't happen when the example is taking a derivative, right? And it's not wrong. It's because there's no algorithm for integrals. You can do them in many different ways. And it could turn out that all 3 suggestions will be able to actually carry them through and get to the answer. Okay? That's why I'm saying it's very important to practice integrals a lot. No algorithm, no correct way to handle this, which you got to know, and that's it. It's just a lot of trial and error, a lot of experience. Okay? So what I chose to do here is pull this 2 out here, and then do it kind of the most elementary way is, right, adding 1 and subtracting 1. Remember we did things like that? But I'm not saying that the other suggestions are wrong. In fact, they will probably work. So I have 2, and now I'm adding 1 and subtracting 1. So let's write plus 1 minus 1 to the top. So I get t squared plus 1 over t squared plus 1. So it's just the integral of 1 dt. Minus 1 over that. So the integral of 1 over t squared plus 1 dt. Do you agree? I just think this is the most elementary here. So what do I get? The antiderivative of this is just t. The antiderivative of that is arctan of t. And then plus c. Do you agree? And then I have to go back to the original variable x. So I get 2 root x minus 2 arctan of root x plus c. And always verify. The appearance of the arctans and the natural logarithms kind of makes it confusing. It's not... If I were to give you this and tell you you have 5 seconds to make a guess, what would be the antiderivative? It's unlikely that you would thought of this, right? Why does that arctan suddenly show up? We know why, because arctan is the antiderivative of something like this, and something like this shows up all the time. Okay? But it's kind of... Guessing this would be seemingly artificial. Okay? So when you get to this, just take the derivative. See that it really gives you this. Okay? To see that you really did it correctly. And it's a one-liner. It's easy. Just do it. Okay. Questions about this? Is it clear how we implemented the theorem by writing everything in parentheses on this nonsense in parentheses under the equal sign? Is it clear? Good? Okay. So I want to write one more example of substitution. I want to use this board. Let's leave the formula here so we can peek at it all the time. So in this example, it's going to be different than all the previous examples in the sense that the substitution I'm going to use is not, doesn't kind of, the integral itself doesn't call for it. Okay, it's kind of, looks like it fell out of the sky. And here's what I'm going to do. I'm going to do the substitution. And this should come under the long equal sign, but it's going to take up too much space. So I'm not going to write it under a long equal sign. I'm going to fill this entire board and maybe half of the next one with it. Okay? And here goes. The substitution is the following. I'm going to write t equals tan of x over 2. Do you agree that it's unclear why I would guess something like this from seeing this, right? The answer is, this is a standard substitution, a standard trig substitution, and one can prove rather easily, we'll see it once we work out the details, that any time you have an integral which contains only sines and cosines, no e to the x's, no ln's, no polynomials, just sines and cosines, and of course tangents, because those are quotients of sines and cosines. Whenever you have a trig-ish integral, purely trig-ish, using this substitution, it transforms into a rational function in the variable t. Always, magic. Okay? And rational functions we know how to do. We have an algorithm for them. Okay? So that's the motivation for doing this weird thing, and let's see how it works. So everything I'm going to write now is all part of the nonsense under the long equal sign. All of it. Okay? Here are big parentheses. All of it is nonsense under the equal sign. So if t is tan of x over 2, arctan of t is x over 2, so x is 2 arctan of t. And therefore, dx is 2, and the derivative of arctan of t is 1 over 1 plus t squared times dt. So do you agree that this is dx? I'm going to put in squares the things that are the take-home message from this example, what you need to remember. And all the calculations, I mean, if you want to use this, you can either rewrite all the calculations, but you don't really need to. If you remember this, you can just use it straight away. Call it the standard trig substitution and just use it without rewriting all the calculations. So this is the substitution. This is what is going to replace dx. Do you see that the dx is replaced by something which is a rational function? Do you see that? Okay. And now, there are some formulas here. So, t equals tan of x over 2. A standard trig formula for the half angle, tangents of the half angle, is the following. Root of 1 minus cosine x over 1 plus cosine x. You can find it in standard formula sheets or trig books or whatever. So t is this thing, and from here it follows, I want to solve this for x. Okay? So t squared is this thing. Let's write it. T squared is 1 minus cosine x divided by 1 plus cosine x. Multiplying out, I get t squared plus t squared cosine x equals 1 minus cosine x. I cross-multiplied. And then putting all the cosines on one side and whatever doesn't have a cosine on the other, I see that t squared cosine x plus 1, so I get cosine x, equals, I'm going to have 1 plus t squared down here and 1 minus t squared up here. So this is cosine. Okay? For our example, in fact, this is sufficient. All we need to know is what dx is and what cosine is. And since we already have these two, we can continue from there. So let's see what we get in our examples. Instead of dx, I'm going to replace it by 2 dt over 1 plus t squared. And instead of cosine x, I'm going to replace it by this thing. 1 minus t squared over 1 plus t squared. This looks like I just moved to China, right? Writing from top to bottom instead of... So, but these two cancel out, so I just get integral 2 dt over 1 minus t squared. And it's a rational function. Do you see that? Almost? Why almost? There's what? No, but what we got is a rational function. Okay? So here, how do we do rational functions like this? We do partial fractions. This breaks up into 1 minus t, 1 plus t. Do you see that? We do the partial fraction business. What we get is integral dt over 1 minus t plus integral dt over 1 plus t. Let's continue on this board. And these are just standard ln's, so I get ln of 1 minus t times the inner derivative, so there's a minus here, plus ln of 1 plus t.
You already did partial fractions.
Yeah.
Okay, you just noted there one.
So over here on this step, I did partial fractions. I didn't include all the calculations, but they're very, very easy in this case. If you want, you can... I mean, verifying that you got the right thing is very easy, right? It's a common denominator. Good? Okay, so do you agree that this is what I get?
Plus C.
Plus C, thank you. This I can rewrite as, right? ln minus ln is ln of the quotient, right? So it's ln of absolute value of 1 plus t over 1 minus t plus c. And now what's the final step? Never forget. Back to the original variable. So ln of 1 plus tan of x over 2 divided 1 minus tan of x over 2 plus c. It's not trivial that the derivative of this is 1 over cosine. Do you agree?
No.
But you can calculate it, and the derivative is going to be 1 over cosine. And
Yeah, but is this like the most simplified form?
I don't know. You can do it so let me write remark. Solve the same example, 22, using a substitution t equals cosine x. This is kind of a substitution that the exercise itself calls for. Okay? You're going to get something different. You're going to get something that looks different. There's no chance of a tan x over 2 appearing in your solution. No chance. There are going to be cosines there. Okay? So you're going to get two things that don't seem to be the same thing, but they are. Okay? The passing from one solution you get here to the solution you get here is going to be via trig formulas. And if you take the derivatives of both, you're going to see that both share the same derivative. So they're different up to a multiplicative constant. Okay? So they're not necessarily exactly the same. They're different up to a multiplicative constant, up to an additive constant. Okay? Do this. Good practice. Okay. So, how did I say what? Here? It's ln of the bottom, but there's an inner derivative which I don't want, so I multiply by it. Okay, just let's go back to the previous board just for a second. Remember I said in this example all you need is the dx and the cosine, but I want to find what sine of x is and put that in a blue box as well, so you can use that too without calculating it again. So remember we said, so t was tan of x over 2. There's another formula for tan of x over 2. In fact, there are several of them. I think 3 different ones. And another formula is sine x over 1 plus cosine of x. This is also tan of x over 2. And therefore, sine of x equals t times 1 plus cosine of x. Right? T is this, so cross multiply, you get this. And instead of cosine x, I'm going to throw this in. So I get t times 1 minus t squared over 1 plus t squared. Sorry, there's a 1 plus this thing, right? 1 plus. And then if you do a common denominator here, what do you get? You get 1 plus t squared plus 1 minus t squared. So you get 1 plus t squared plus 1 minus t squared. So you get just 2 times t. So you get 2t over 1 plus t squared. Do you agree? And this is sine of x. So let's put this in a blue box. So you can see that all the ingredients that you're going to substitute if you use this substitution, and in fact you never really use this. You don't use this. You just use the dx, the cosine, and the sine. And they're all rational factors. So when you work with them, you're going to get a rational function. Always. As long as there was nothing else. If there was somewhere an e to the x, that's going to mess up everything. Don't use this substitution when there's an e to the x or anything other than just cosine, sines, or tans. Okay? When there's anything non-triggish, this substitution will make a mess rather than help. Okay? Okay. Good. So this is what I wanted to say about substitutions. You still have to practice a lot. I'm only going to say that 5 million more times. I want to do one last example for indefinite integrals. And then we'll do the break. And this example I'm going to dedicate to our friend Plessy here. Because so far in everything we did, it seemed like remembering to write the plus c is just a burden. Okay, don't forget to write the plus c. But I want to show you that this plus c has a meaning, a meaningful meaning, and that it's not just something not to forget in order to make it accurate. So this is example 23. Suppose we want to find the antiderivative of e to the minus absolute value of x. Okay? So, how do we do this? Well, what is e to the minus absolute value of x? E to the minus absolute value of x, whenever you see an absolute value, you can rewrite it as a case function and separate the cases where x is positive and when x is negative. So when x is positive, this is just the function e to the minus x. This is when x is positive or greater than or equal to 0. Do you agree? When x is negative, the absolute value of x is minus x, so we have e to the minus x, so we just have e to the x. So this is the function we're looking for an antiderivative for. Do you agree? Everybody? So what's the antiderivative? What's this the antiderivative of? Well, whenever x is non-negative, we're looking for the antiderivative of e to the minus x. And the antiderivative of e to the minus x is what? It's e to the minus x times minus because of the inner derivative plus c. Do you agree? Whenever x is negative, we're looking for the antiderivative of just e to the x, which is just e to the x. Good? So we just found the antiderivative for any x. Would it be justified to write that this function, okay, would it be justified to write this equals minus e to the minus x plus c when x is non-negative, and e to the x plus c when x is positive, when x is negative? Is this correct? Let's draw it. Let's draw it. I mean, from our calculations, it's kind of, that is correct. We just found the antiderivative on every subinterval, glue them, and there you go. But look what we got here. Let's draw these. So what's e to the x on the negative ones? E to the x looks like this. Do you all know this? Looks like this. This is 1. And then it continues up here, but I don't want that, right? It continues to go up here, but I just want e to the x for negative x's.
Shouldn't that value be c?
Wait. Do you agree that this is e to the x?
Yes.
Do you agree? Plus c means that I can take any representative, move it up and down, and it's still going to be correct, right? What is, wait, 1 second. What is minus e to the minus x? E to the minus x looks like this. Do you agree? We're not interested in what it is on negative values, so on positive values, e to the minus x looks like this. Do you agree? So minus e to the minus x looks like this. I'm just taking its negative. So this is, okay, here we said there's a whole, because we said for x greater than or equal to 0, we're taking this value. So this is minus e to the minus x. Do you agree? Everybody? So is it true that this is an antiderivative of this? It can't be, because this is not even continuous. If it's not continuous, it's definitely not differentiable. And it can't be an antiderivative of something, because an antiderivative is something whose derivative is this.
Here, plus c has to equal c.
Right. I need to use the plus c. The plus c doesn't work separately on these two. I need to use the plus c here in order to find a continuous function whose derivative is this for positive x's and whose derivative is this for negative x's. How do I do this? I'm going to need both hands. I'm going to take these two and do that till they glue correctly. Okay? And I can do it because of the plus c freedom. So I'm not going to take this. Instead, I'm going to here, let's erase these dots. I'm going to take here this. This is going to be minus e to the minus x. This was minus 1, this was plus 1, so I'm going to add 2. And throw this away. Now I have a continuous function, whose derivative for any x is precisely this, then you can verify that. Okay, so this is incorrect. I'm going to replace this by, so what did I fix? I fixed this. I added 2 here. And now I'm going to say, okay, once I have this entire thing, I can plus c it freely. It's going to have the same derivative. So now I can write plus c here and leave the plus c here, but it's important that it's the same c. So I'm taking this entire thing and I can move it up and down and it will still have the same derivative. Did everybody understand what just happened? Okay, do you see the crucial role played by questions? Yes?
Can we do that for any function which we have jumped this continuity then?
Not necessarily. Okay, that's a good question. Can we always, suppose we have a function, we find 2 candidates for being the antiderivatives on 2 different intervals, can we always glue them together? The answer is, you can always glue them together by moving them and making it continuous. But what may not happen, what could go wrong, is that you want it to also be differentiable at 0. Remember, this is a case function, right? In order to prove that it's differentiable at 0, you can't just take the derivative of this, and you can't just take the derivative of this. What do you need to do? Right. You need to go to the definition of the derivative with the limits and check the one-sided limit from here and the one-sided limit from here and argue that this function is in fact differentiable not just here and here, but it's also differentiable at 0. And you have to prove that by definition, and you'll see that it is, and that its derivative at 0 is 1, which is precisely e to the 0, and therefore its antiderivative is in fact this on the entire real line. Okay, that takes more work. Okay, so remark, need to show that, so let's call this entire thing star, that star is differentiable at x equals 0. That does not follow from the things we did so far. You have to check that separately using the definition. And in case it doesn't happen, if you try to glue two things like this, and you have a cusp, then it's not an antiderivative. And we had examples like that. In the very beginning, when we started talking about antiderivatives, we said, hey, not every function has an antiderivative. Remember? And we said, okay, take a function that looks like this, like 1 and 0. And we got that the antiderivative, no matter how we play with it, has a cusp. Therefore, it's not an antiderivative. Yes, question?
To do this, like without the graph, you would just plug in for x equals 0 and then find the difference between the two?
If you wanted to set this right without drawing it, you would still need to in your mind, see that you need to make it continuous. And you do that by looking what the limit of this is as you approach 0 and setting it equal to what you get here. But still, you would always need to do this. Okay, more questions? Okay, so this is an important example. I really feel like doing one last fun example. Let's do one last fun example. Very short. Define fun. Isn't everything we're doing here fun? Yes, it is. Yeah. We're having fun, aren't we? Hey. Okay. So here's one last example. So this is number 24. Suppose I want to find the antiderivative of tan x. Okay? We did this. I know we did this. I want to do it again. So I'm going to write it as sine x over cosine x. Cosine x dx. And what we did is we said now it's ln of the bottom, remember? And it required some fixing, and it was minus ln of cosine x in absolute value. That was still correct. I just want to do it again differently now. Okay? So I want to do this using integration by parts. And the parts are going to be, so v prime is going to be sine of x, and u is going to be 1 over cosine of x. Do you agree that this is legitimate parts? So what do I get? V is going to be minus cosine of x, right? And u prime, the derivative of 1 over cosine, which is cosine to the... Why did I write u squared? U prime, so cosine to the negative 1 is negative 1, cosine to the negative 2, sending it to the denominator, times the inner derivative, which is minus sine of x. Do you agree? So the minuses cancel here, so I just get u prime equals sine of x over cosine squared. So all of this was my integration by parts. Good? Everybody follow? So what do I get? I get u times v, which is minus 1, u times v minus 1, minus the integral of u prime v. But u prime v, so it's minus cosine times this thing, so that makes it into a plus. The cosine cancels with one of these, so I get sine x over cosine x. Do you agree?
Is the difference, like, on tests and things, if we would write, like, v prime and sine x, you write v prime equals sine x dx, or it's not?
No, 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 no. Here the dx does not play a role. It's not like in the substitution formula. The dx is not part of one of these. These are just the two functions.
Isn't the derivative, wouldn't you write, like,
The derivative of sine is minus cosine as a function of x.
No, the derivative of negative, okay, so you
No, 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 sorry. This is the v prime. The derivative of minus cosine is sine.
right, so you don't have to put in any of the...
No. There are other ways of writing. Some people write d cosine and all kinds of things like that. This is the way I chose to present it, and I don't want to confuse people with other ways of writing. If you know other ways of writing and you know how to do it correctly, that's fine. But I want to stick to one way and not confuse everybody with other ways. Okay? Does everybody agree? Look what I got. Tan x, which is this, equals minus 1 plus the same thing. Move this to the other side. It becomes a minus. So conclusion, 0 equals minus 1. So people here are giggling inconveniently. Oh, this is cool. This is really cool. You can now go to the bank. Suppose you owe them minus $1 million. You say, hey, we're even. In fact, you can go and say, wait, don't you have to give me $1 million? So what just happened? What went wrong? Something went wrong, unless everything went wrong since we were born. So more likely something went wrong here. What went wrong? Are we having fun? See? Told you it's going to be fun. So what went wrong?
You had that minus 1 there, just because.
No, I used integration by parts correctly. What went wrong is plus c. That's what went wrong. When you say that the solution of this is minus 1 plus this thing, we're implicitly saying, okay, there's a constant. It's going to show up after we solve this. That's why we never write it at this point, and we add it after we solve this. Do you agree? Okay? But now we did something different. We moved it to the other side. We canceled it. So we kind of forgot that actually there was a c here. Okay? And it's true. It's true. 0 equals minus 1 plus c. This is true. And remember what this 0 is. This 0 is not the number 0. It's a family of functions who share the same derivative. So the constant family of functions is the same as this constant family of functions as long as you add a constant. This is true. The bank won't argue and say you still owe us 1, whatever. Clear? Okay. So this is the importance of plus c. Now you know you're important, our dear plus c. And this example and the previous example should convince you, and we'll encounter plus c again in significant roles in the future. But remember, writing the plus c is not just, it really encodes a truth that is important, okay, and not just something to write for the sake of completeness or whatever.
So we would have
have to choose in this case c equals 1?
No, this is not the number 0. This is a family of functions which you chose to represent by the constant function 0. This is the family of constant functions, and as is this. That's the plus c. Okay? So it's not that plus c needs to be 1 here. It's the family of functions, constant functions, equals the family of constant functions up to a constant. That's the statement. Okay?
So actually just say something.
This says nothing, I agree. And we, in fact, using this solution, we didn't solve this in particular. Okay? All this example does is to illustrate that plus c is important. Okay? But we know how to solve this, right? We did it. We did it before. Okay, let's have a break now. And after the break, definite integrals.